So in this video I'm going to go over the user controls for this computer. I'll go over the actual circuit description later in the video, but the actual visual controls are the upper address byte, which is a series of 8 LEDs, the lower address byte, the data byte, and the control signals from the CPU itself. So I've got a set of switches as well, and some slide switches. So I can set a value on the slide switches. There's eight slide switches, but everything's ignored on whatever I do on these switches while the computer's running. And as you can see, it's currently running the program. So I have a slide switch over here to put it into user mode. And when I put it into user mode, it does a bus request to the CPU, and then the CPU responds to the bus acknowledge here. And when that's lit up, then you have control over the actual data bus and address bus. You don't actually do anything, you don't manipulate the CPU in any way, which I think the Altair 8800 does. What you do is you actually just manipulate what's in RAM. So I've got the RAM chip here, which is 128k RAM. And you can set the address byte. So if I slide the switches here to a value I want to go in the RAM, and I can load it into the upper address byte there. By doing that, then I can change the value to something else, and I can load it into the lower address byte, like that. And then what's in that address in memory is displayed on the data bus. And I can, here there's an increment button, but I've been moved onto this board at the back at the minute because I've used a multi-stable multi-vibrator, which will go in the circuit here in the second revision of the board. So the increment button currently is this switch here, and it increments the address through the address values, and you see the data values change into what's in the current RAM values. And then the other button, which would be here, and it was going to be here as well, but I've combined those two buttons into a single button, which in the second revision will go here, and that takes whatever you put in the data bus. So if I just put some value there, and I press the button here, it then loads that up into the data bus. So if I increment to the next address, then I can load the same value back into the data bus again. Increment to the next address, I can change the value I want to go in there, and it doesn't show it only shows you what's currently in RAM on here until you write some new values to RAM, and then it shows you sorry, that was the wrong button, this one, and then it shows you what you've written to RAM, and then you increment here. I've put them together, the buttons on a kind of a logical area here. So I've got the high byte where you set the high byte of the address here next to the high byte where you see it, and then where you set the low byte of the address next to the low byte where you see it. And what would be the increment button, which is currently here, goes next to the address at the lower thing, so that it's logical as to what buttons are associated with the address. And then the set and the set and write to memory button is there, and so that's logical next to where you set the value, and you see the data value, new data value, in the button down there. If I've got a reset button for the CPU here, and it resets not just the CPU but the counters, so it goes back to 0, and I can put it back into run mode. And as long as I haven't changed anything in memory, the program should start running again. It's the kill the bit program, so you just should see a rotating LED on there. So there's a kill the bit program running. If I switch the button up, then you see it changing exclusive or in the data on the upper address byte. So normally when I'm developing something, I'll create a single-sided board like this at home, and then I can resolve any issues before I get the full printed circuit made at a manufacturer, because it takes a little while to get the manufactured boards to come back to your address. But I couldn't get that done with this board because it's double-sided for a start, and I can't really make double-sided boards at home, and it's quite complex as well. There's lots of tracks going all over the place and wires and things like that. So I didn't really want to send off for this unless I was reasonably confident that I could actually make it work. Now most of the CPU stuff like this and the support chips, the wires go directly from the CPU to support chips, so there's not really that much that can go wrong. So I wasn't too worried about not testing these. That would be a lot of wires to wire up to test them, and to get the CPU working. It was is work that I was willing to to not bother testing. But these counters at the front, I've not used those counters before. I wanted to make up the circuit to test those and to test the output LEDs and read it and write into the RAM as well manually, because I wanted to make sure that worked before I got this board produced, because otherwise I'd be wasting my time. And I'm glad I did, because this is what I produced to actually test it. Now, it's really quite messy, and but all I needed to do was prove the concepts and make sure that the features worked. And over here at the back, I've got the red LEDs are the upper address byte, the amber LEDs are the lower address byte. Now, you're not going to be able to see this very well. The green LEDs over here are the data byte. I've got a memory chip over here, which is a 128K RAM. And I've got the dip switches here, which simulate the switches, the slide switches on the board where I enter some information to be put into RAM. And then I've got the load high address of high address byte and load low address byte. I've got the load data byte, and over here is the write data to RAM byte. So those two have now been combined on the final board, but for testing purposes they were separate. And in amongst here I've got an increment address button, so I'll try and press that now. So I'll show you so the address at the back here will increment as I press the increment address button. So that proves that. And then I've got a reset button over here, so that resets the counter, so you see the address go back down to 0. So that proved that I could, because it goes across four bit counters, the actual address. So I had to make sure that I could reset all of those synchronously. And then I wanted to test, so if I put a value on the dip switches down here, loading into the high byte of data, of address RAM, address bus, loading into the low byte address bus, and then loading into, just make sure that's a different value, loading into data bus, which you don't get to see updated until you write it to RAM over here, and then it writes to RAM. Or I could change the value and load it into RAM, and that proved that proved that the actual circuit was viable and it would work. And so I felt better send off the PCBs after all that, and so that was a lot of work to put all these wires in it. It's a mess, and it won't mean anything to me now looking back on it, because that was a few months ago that I made this, and I'm going to take it all apart now because I've got the boards through and they worked fine. And so that was a relief. That if I hadn't have done this and I just made the boards, I would have got it wrong, because the way that the counters worked weren't as I thought they would, and the boards that I would have got wouldn't have worked to the degree where the boards would have been useless. I wouldn't have been able to manipulate the tracks to make it work. Whereas the way I have had a few things that I needed to resolve on here, but I've been able to cut tracks like that, individual tracks, and there hasn't been that much that I've had to actually alter, and I've managed to test all of the circuit. Just need to test this socket next, and that's the final thing to test, but the rest of the circuit's been tested, and so I'm almost ready for issue 2 of the board, and that way hopefully I'll be able to then progress into more complex things with this board. So these are the counters I'm using, 74LS163s. They're 4-bit counters. As the address bus is a 16-bit address bus, you need 4 of them. So 2 to represent the high byte and 2 to represent the low byte. And also, it's got inputs as well as outputs. So when you clock the load, it will load the counter with the value you want. So that's what I need in order to set the high byte of the address bus and set the low byte of the address bus. So I can go to any point in the RAM which I want to. They also ripple through, so it's got a ripple out, so you can ripple into the next counter. So at the bottom of the data sheet, there's a typical applications diagram, and this is all I needed actually in my actual circuit. So you've got inputs to the counters at the top, and then you've got a load clock, which you can load and address into the counters. And now I needed to tie 2 of those together, so I could set the high byte, and 2 of those together so I could set the low byte, and control those individually. There's an enable, a counter and an enable, we'll just hold that high. There's a ripple through which goes from one to the next, and you just hold the first one high, so it automatically ripples through. And that was the weird thing about this. The clocks, this is what I didn't understand, and what would have made it not work if I'd implemented it. You clock all of them at the same time. So the counters I'm used to are at 74LS393s, and an output from one goes into the clock of the next one, then that's how it ripples through. But this works in a completely different way. So when you increment, you have to just increment the clock signal, and that increments all of the count. Well, it increments the first one, and then it will automatically ripple through. And also, there's a clear line which I can connect to my reset button on my computer, which will also reset these counters as well as resetting the CPU. So this is how I drive the LEDs. So each one is an HCT245. It's just a buffer, and it normally drives data buses and things like that, but actually the outputs can drive LEDs, and I just have the LEDs on the outputs. Putting through a 220 ohm resistor ladder, so I've got 8 resistors in one pack, and on the input I just have on this one the address lines, the high byte address lines, on this one the low byte address lines, and the output from the resistor pack goes down to 0 volts. So this buffer is sourcing the current. And then over here I've got exactly the same for the data bus here. And then just the one other one which is worth pointing out, which is the remaining one, the control bus here. Again, I take the control lines into the buffer, LEDs on the output. But on this particular one, the LEDs are the other way around, and if you follow the resistor pack, it gets pulled high. And that's because these lines are inverted. And so to make a more logical representation of them on the LEDs, I invert them so that when the LED's on, it means that the line is active. Otherwise, they'd all be on and only be active when they go out, and that's not so logical. And that's the good thing about these buffers, is that they can source enough current and sink enough current to drive LEDs.